Assalamu alaikum. So this is Dr. Bilal Wajid. Greetings. Now this particular chapter pretty much talks about pre-processing, and it's technically all about filter design, whether that's low pass, high pass, band pass, Butterworth, smoothing, sharpening filters. Technically it talks all about pre-processing stage, and in this particular section we're going to talk about filter design and just introduce some basic concepts. Now filters are in fact important. They're not just technically limited to images or frequencies. In the last, for instance, lecture we moved from one-dimensional Fourier transform to Fourier tree series to discrete time Fourier transform, and then discrete Fourier transform, and then we moved to two-dimensional DFTs. So in other words, even in images you have a two-dimensional discrete Fourier transform. So there are frequency components that need to be filtered for any reason whatsoever. A common filter that you use on an everyday basis is your spam filter in your emails, or any of the advertisements that have a tendency of occurring randomly. You may want to filter those out. In your phone calls there is something called blocking a number, whereby which you block numbers of people you don't want to talk to, or messages coming from people you don't want to listen to. So there are three types of filters. There's low pass, band pass, high pass filters. And a low pass filter, in some sense, this is an ideal low pass filter where all the frequencies up until D0 are allowed to go from the input to the output, whereas all the frequencies beyond D0 being your cutoff frequency, is not allowed to go ahead. This is what the system looks like, where H of S is the impulse response of this and Q of S is the output. So this is an ideal low pass filter. An ideal high pass filter would look like this, where beyond D0 all the frequencies are allowed, whereas before D0 they are eliminated. This is a band pass filter, so it only allows frequencies within a particular band to pass them through the system. Now these are examples of ideal low pass, high pass and band pass filters, and they're hard to make. And some good approximations are Butterworth filters. So Butterworth filters look like this. They are maximally flat in the allowed zone and minimally zero on the zone which is present in cutoff. So this is a low pass. You can see in the allowed area they're maximally flat, and this is a high pass filter. So the allowed area they try their level best to achieve to 1. But the transition here from allowed zone to not allowed is a smooth transition. Now generally the cutoff frequency, again this is just taken by standard, is the cutoff frequency at which it is the magnitude reduces to 1 over under root 2. Now Butterworth filters are made by, this is the equation of the Butterworth filter. So it depends on the order, so you can complicate it, and the more number of terms you use, the better the impulse response. So for instance here you can see if the order is 1, it slopes slowly, but if the order is higher you can see it slopes down much quicker. So Butterworth filters do have, as you can see, there is a complex there is a J here, there's an imaginary component. So they have a real component and they have an imaginary component. Or you could say, with respect to frequency, they both have a magnitude response and a phase response. Together is what their response looks like. So the higher the order, the complexity increases, but also the output. The filter does become much sharper and better as the order of your filter improves. Generally in MATLAB, you would use this equation, butter, NWNS, where N stands for the order, like we mentioned here, N minus 1, you know, up until whatever order you want. Wn is what is here referred to as the cutoff frequency. You can see here there is a cutoff frequency D0, right? There is a cutoff frequency D0. And the last thing here is whether it's a low pass or a high pass band pass. So you can put high and low as well. So one example would be N10. So this is the Butterworth filter, which this is a low pass Butterworth filter of order 10 with cutoff frequency this. And you can plot their frequency response using this term. Now this is a command in MATLAB. You can use frequency Z, where you put the same components of B and A, and 128 and 1000. 1000 is the sampling frequency and 120 is the number of points. So that's pretty much for this lecture, this part. Again, all we discussed in this component was introduce what an ideal low pass, a high pass and a band pass filter is, and that, you know, it's hard to come up with these filter designs in actuality. So one very good approximation is a Butterworth filter. And Butterworth filters you will see in the next lectures as well. They will keep on coming. The generic equation you've seen, this is what the generic equation looks like. It has an order associated with. The higher the order, the steeper would be their flow from allowed zone to the zone which is not allowed. So the steeper the better. And that's pretty much for this lecture. In the next lecture, we're going to talk about image enhancement. Thank you very much. Assalamu alaikum.